Okay, so let's start. No, nobody wanted number one, so okay. Maybe let's just skip it then. For now, if you will have time, so then I'll do it on the board. And so number two, let's see. Maxim пришел.
First, we need to calculate this thing. Let's rewrite this as definition. This is definition of this defines as this.
Yes, okay.
Just
This is the definition of dpi.
yeah, it's just definition of dp.
Yes, okay.
So, and we want to write definition of this thing. Let me also write this horizontal here. Actually, we want to calculate it at point P. I think it would be so we know what this horizontal P is. It's just the inverse of this on the horizontal.
Yes, so
This is restricted on horizontal part of T. So this is just ID. So we can. Oh, I forget about. And so we can rewrite it as P at the point.
yes, so core is defined exactly as right inverse, right?
Yeah. Our definition was this. This is P is when pi in T. So this is just the ID on horizontal. So we can write this. V is so we need just to choose correct point. So we need to take this as a point, and it's what we need to. That's all.
Okay.
The first part. So second part, we want to compute both H something of commutator.
So it's called horizontal.
Horizontal lift of commutator at the at this thing. Yeah, that's f is an arbitrary smooth function on x. So we just need to use this quality. So we get that this at the point of composed to P. And then we want to calculate commutator of horizontal lifts at the same thing. Okay. This is my definition of commutator is minus in the hour order now we just use this equality again. These two things are smooth functions, so we can use our equality again and get so these things are the same by definition of commutator.
These things are the same, right?
Just think of the commutator as
Right, yes.
this thing minus this thing.
Uh-huh.
Oh, but when we check that this thing and this thing equals on functions like that,
Right.
so we need to check that there, if we set we define v as we need to prove that this is horizontal because it's horizontal lift of something, and we want to check if this equals the horizontal part of this commutator. So we need to check that if we have some vector field V on then where is on the vertical component? No, there this thing minus this thing is equals to 0 on each function. And
So maybe you can write, so if v is 0, then what? Then it is only horizontal.
yes, the V horizontal.
Yeah.
Do just
So maybe write the statement. So this implies that v is horizontal.
I just prove it. Me. Okay. Let me another time revise this thing as p where equals to 0 at any function f equals to 0. It's this thing we define as this. So
And this is for any function f. So therefore this
this is a function from infinity x to if I'm not mistaken. So and it's 0 for each function. So just 0.
Yes.
It means just that v is in kernel of dp. It's just a definition of v. So the things different only in the vertical path.
Right. So if you take h, they're equal, and the h of the first thing is just this thing itself.
Yes.
So let's write it down so to get
Okay.
everything here.
Okay. H from it's just the same thing because it's a horizontal rift and it's
H of difference is 0, right?
this is the same thing because we just not this is exactly the same. We just prove that if on these functions they are the same, then they different only in horizontal. No,
Only in
only vertical
Yes.
component.
Yes.
So
So we're done.
yeah, and what we need to prove in the third. Oh. Okay. Horizontal part of sine h dx h as we proved in the second. First, commutator of horizontal lift of their commutator. And but these things about h is just 0 because commutator of is so it's 0. And we want to use that. Goes to 0, the curvature is 0, means that if h of eta equals to 0, and we want to take c equals to dxih, eta equals to ddjh. They are horizontal, so H does nothing. This is just the commutator, and we get that vertical part of this commutator also 0. So the thing 0. That's all.
Okay. Let's talk about this.
Можно попробовать.
Да.
Okay, if we want to restrict Euclidean coordinates to the two-dimensional sphere, we will have such expressions in terms of polar coordinates. Then we should have such metrics. And we want to restrict it to the sphere, and we write in polar coordinates. So I will not write all the computations. Some answers. It is very similar. We will have it will be the same thing here, but with the
Sin and cosine for phi changes. The changes, right?
yeah,
And maybe some signs.
some sign here.
Uh-huh.
And so
Yes, that's
so
very
we
important.
will be plus theta theta plus square theta square and the square is easy. Just square theta. So now we can see this term, and this term adjusts cosine square of theta. Then we have sine square of theta here, so it will be just 1 if you sum all this. So sine square, this one, and with this one. And here we have sine square of theta, sine square, but not, should be not cosine, but it should be sine, of course. We only need to change function with the phi.
Yes.
So here sine square plus cosine square of phi is just 1, so the answer is this. So we actually don't have cross terms with theta and phi. So if we have 2 points A and B, the length, the distance between these 2 points is such an integral. decided to think about phi as a function of theta. So we will think about our path as a function, as a phi function of theta. So if theta does not change, we can just rotate the sphere some way to make phi change. I will use some mechanical, some variational approach to this problem. We proved on the last seminar that we can have geodesics equation from the earlier Lagrange equations. So I will use this approach here. Okay.
So okay, just understand. So if I have four, so phi, what is theta and what is phi? So phi kind of measures angle if I goes. So
theta, phi is angle here. Theta, this one is this.
Okay. So if I go like from the North Pole, right? So if I have like an exponent, say something like exponential map from the North Pole, right? So if I go and change theta, so theta is kind of radius, right? And phi is kind of like a sphere around it. If I change it, okay.
Okay. So then our length is an integral from theta A, theta B. So it's theta at the point A, theta at the point B. By rotating the sphere, we can take them. No, we will do this first. But no, by rotating the sphere, we can make our points have the same phi, for example, or something. Maybe no, we don't think about it. Okay. So the integral.
So phi is a function of theta. No, okay. Well, you first can concentrate on these curves, maybe. Then see that others they just should be longer, kind of, because it goes like. Yes.
So okay, then our length can be written as this integral with the integral variable theta. And it means that we have Lagrangian 1 plus sin square theta where phi prime is theta. So theta plays a role of time in this case. Phi is the coordinate, phi prime is the velocity. We compare it to mechanical system. Okay, then we have Euler Lagrange equations that, of course. Yeah, and because we don't have cross terms, our Lagrangian actually does not depend on coordinate, on phi. So phi is equal to 0. Phi is called like some cyclic variable, or something like this. Then
you have conserved charge or something.
Yeah. Is just constant on theta. So let's count this derivative, partial derivative. We get sin squared theta prime. We have 2 here, but we can take it into the constant. Some constant c. Yeah, now let's find phi prime in terms of c and theta. Phi. Then phi prime just and now we can find phi just by integration of this expression. And to integrate it, we need a change of coordinates. Let's take some variable u to be cotangents of theta, then du is minus 1 over sin squared theta, d theta, square theta, du. Put here, and we have phi minus c minus c. Here, we can put this sign in the numerator under the square root. And so it's square root theta. And now we need to express this root in terms of new variable u. Oh, and integration here. Change the variables already. Yeah, so this is equal minus integral du 1 minus c squared theta. Let's look at u square. Theta, then 1 plus u squared is just 1 over sin squared theta. And
So it's 1 minus.
yeah, c du 1 minus c squared minus c squared. So we have an integral from the table. It's an integral of arc cosinus, inverse of cosinus, cosine, and you write this square, denote it as a square. These constants here, and it will be. Let's see. And it will be arc cosine u over 8 plus some constant. So now what we have,
So this is a phi as a function of theta.
theta, yeah. So we have phi minus phi naught is minus And let's understand that this thing is the big circle of the sphere. So if you have some plane, Ix plus b plus c here, it will be 0. Then we need to put restricted to the sphere.
Just plug in spherical.
Then we can put this into the left side. Theta, then divided by sine of theta. This one is minus c cotangents of theta. And the sum of cosine and sine can be written as some constant or sine phi minus phi 0 minus tangents theta. So divide by minus c and rewrite constant c2, you get the same equation. Not u, but theta.
Okay, yeah, thank you very much. So, yeah, I of course don't know how to take such integrals, or forgot. So actually, practical idea what can be deduced from that.
Apply transformation from SO3 transform random arbitrary great circle to the great circle which goes through the North Pole, and then to check the circle that goes from the that contains North Pole is a geodesic. It's much easier because
You just check it, right? Yeah. Well, you can do this or also like a general statement. So suppose that you found maybe this. Suppose that you have point P and you have a neighborhood n, like you have some neighborhood inside your manifold, and suppose that you found a diffeomorphism like this. So this is unit sphere, or whatever, just sphere. This is interval, open interval. So suppose n is such that you found like a spherical coordinates, so to say, n, but I would like to delete point P. And suppose that I found such map that phi star of G is actually well, dt plus some function times d omega, well, omega, which is well, rather like this, something like this, where so here sum of I, right? Omega squared, something like this. So this is what it means that there's no cross terms, right? So suppose that I found such map that my remaining metric looks like this. Then I just can apply the same analysis as we did in the lecture and see that the paths of minimal length coming out of zero just look at as straight lines going along radius, because like it's just the same exact the same exact analysis says that if you go like that, then this will give you like more into your length. And then you're done, because you know that locally geodesics minimize the length. So if you're lucky enough to find something like this, then you know what a geodesic is. And so that's what's going on in surface. In sphere. Okay. Let's proceed and I don't know, 10.4. Maybe Alexander Kirill.
We can animate geodesic on this manifold extend to the whole power. Okay, let's assume that we have geodesic that defined not only the whole R, and let's assume that it defined on the interval from 0 to B. Okay, we can let's it's gamma of B, and that U will be convex neighborhood of R. We can say that there exists A.
The convex, what does it mean?
Normal, I think. Normal, not convex.
Normal in the sense that exponential is diff of 2u.
Yes.
And there is like an inverse of exponential.
Yes, I think normal. Yes.
Okay.
Normal. We can take A between 0 and B, such that the image of interval from A to B in the A or in the U. Let's gamma of A will be P, and we can, because of U is normal neighborhood, we can say that exists for V the inverse of exponential at the point E of R of gamma of B.
Gamma of P. Yes, okay.
So
R is gamma of P.
U is open, so So, x
Okay.
x inverse of u is open, so there are so exist null t0 more than 1 such that t0 v.
I'm a little bit confused because you have normal neighborhood of R but take exponential inverse at P. So usually if I take a normal neighborhood of some point, right, I take exponential at this point as well, and so for each everything that lives.
Okay, I want maybe I want neighborhood of P maybe.
You maybe need neighborhood of R, it's okay, but you take exponential inverse of gamma of A, of P. That would make more sense for me. So x bar of gamma of A. So I don't know, let's draw a picture. So you're saying what? Here's your curve. So this is what, gamma of B, which is R, right? This is R. And you're saying, okay, let's consider normal neighborhood.
Yes.
And then take a point inside this normal neighborhood. P. So I would, if I consider normal neighborhood around R, I would take exponential R or inverse of any of these points here. So that would be like natural for me. But you take an exponential.
Maybe of R. Maybe.
Yeah, but what of what? So if I take of gamma of B, this will be just 0, right? So I need to take of this maybe.
Yes.
And this will be my B.
Yeah, maybe yes.
I'm confused why you need a P at all, because like if you take this normal neighborhood, right, this piece of geodesic is just a straight line in normal coordinates, right? So you just take straight line and you continue, like you just continue it like this. So you don't need to repeat.
Maybe yes.
But okay, let me not.
And we can say then we have this geodesic,
Right.
and we can say that it acts by this, because we have only because of uniqueness of geodesic from one point to another. If we restrict our geodesic to this interval.
I think you forgot to write the exponent before the...
Oh, yeah, of course. X of this thing. And it restricted on the T from A to B, but we can extend more than B to the from A to T0 B minus A plus A. And T0 more than 1, so it's T0B minus A T0 minus 1, so it's less than B, or it's more than B. So we can extend our geodesic from this interval.
Yes, okay. But so it seems for me that you actually want your neighborhood to be around P, right? And you want P to be close enough so that this normal neighborhood will contain R. So it's a little bit different situation, but it's not clear why you can even do this, because like, okay, there exists normal neighborhood around each point, but maybe as you go, you know, closer and closer to R, it will, so normal neighborhood will be like smaller and smaller. And so each time, as you reach R, your neighborhood is smaller and smaller and smaller, and so you never can get this. So there's some problem, but I don't, so if you have something like this, you don't even need P, right? You just take normal neighborhood of R, don't need, even need point P, right? You consider like a piece of geodesics that is like that, and of course it has, so you have it, you just take this tangent vector to R, right? And in normal coordinates, you just consider curve, right, which is given by this direction, just straight line, right? And it should coincide with this piece of geodesic that you give. And so you continue like that. There is no question here. The question is why you even can. So if you have maximal geodesic,
Yes.
it means that there is this maximal open interval.
While we can extend it to closed interval.
Yes, that's the whole point. So because maximal, so when you solve like a differential equation, right? So maximal existence, like it's local, and local means that it exists on open interval, right? So maximal geodesic is something like defined on open interval.
But if we have on the open interval,
Yes.
we have compactness, and we can consider sequence.
The Cauchy sequence.
Yeah, with the Cauchy sequence, and we can say that it's convergent sequence. So we can.
So gamma of B actually exists because it's compact manifold.
Yes.
And that's where you actually use compactness, right?
Yeah.
Otherwise you never used it.
Yes, of course.
Yeah, okay. And that's the whole point. Okay. Okay, so we have time. Let's do five. Кирилл, давайте вы.
Yeah.
we have a curve from 0, 1 to m, and we have the initial conditions. And then we can say that gamma of one laser sphere with the radius epsilon and the center p, which means that the distance between them is epsilon. And we can prove that we have the length of the curve is more or equal than epsilon, and if we have inequality here, then gamma is general. So without loss of the generality, we can say that gamma of t is not equal to p if t is from 0 to m, because if we have such a situation, we can construct another curve, which is we can construct a curve such that it is p0 and in 1 it is equal to gamma of 1 is equal to q. And well, when we construct this one, we can prove this thing for this curve. So now we can then
Gamma tilde of 1 equals gamma of t.
of 1. Yeah.
Well, of the first.
Yeah. So we can suppose then that this curve actually lies in the ball, this ball, and we can let the gamma of t be x p and c, where and c be the.
So by the way, still not clear why you can say that it's in the ball. Because it might be go outside of the ball, but not hitting the point P, right? And then you can. Well, so far your condition is that
Yeah.
it hits T at the first point, like at the first point, is weaker than it does not leave the ball.
Well, then we can prove like the same thing for the curve. Like if we have such a situation that P is here and P is here, and our curve is just like that,
Yes.
we can take this point and prove the same thing for the curve, for this curve.
Yes.
And then if the length of this curve will be epsilon, then the length of this curve will be more than epsilon. And
Yeah, this will mean that it's geodesic inside B epsilon.
yes. So we
But then we need to prove that it's geodesic everywhere.
well we use like the same thing like we have here. Like we construct another curve, which is equal to the curve gamma in the ball.
Yeah, maybe you don't even need that gamma lives inside
Well,
B
yeah.
epsilon. Let's just proceed.
So we have the NC in the sphere, and it is defined for C from 0 to 1, and RT is defined for from 0 to 1. Yeah. Then we can calculate the derivative, and will be before the exponent.
So we have gamma of t is like this.
Yeah.
Yeah, well, you really need then b epsilon to be
Yeah,
normal,
we actually,
right?
yeah.
But then you actually can. Okay, so what's the what is the conclusion so far? Okay, let's just continue, right? And then let's see.
So, well, now we have that we know that the first product of NC is equal to 1 because it's on the sphere. So then the derivative is equal to 0, and therefore this vector is actually tangent to these to our to the sphere. And we can then write that because of that the NC is so then that's referred to the point, then we can write that the derivative is actually is equal to something like this, where the right t is equal to and now using this equation we can write the length of our curve. So it will be the integral over section of equivalent in the power of 1/2. Which is equal to this, and then we can say that this is obviously more or equal than the integral over the derivative of the RT, because actually if this is not 0, then this will be more or equal. So, and this thing is equal to epsilon. So now we can see that actually the length of the curve is more or equal than epsilon, and we have that the equality here holds if and only if this thing is equal to 0, and if it is equal to 0, then by the definition of it, we can see that the this thing is 0, meaning that n of t is a constant. So, and therefore we have that our curve equal to something like this, which is the so like it has the constant velocity.
Well, it's just by definition of geodesics,
Yeah.
it's geodesics.
Yeah, that's it.
Right. So, but well, if you change, well, I guess r of t, you get you need a different parameterization, which is r of t.
Yeah, it's like
Yes. Yes.
a reparameterization.
Yeah, but actually, we
So
like
we-
in lecture we proved that if you have like locally geodesics minimize the length, right, and we proved it basically this way.
Mhm.
So now the question is that okay, so locally, okay, you have this, but now you're taking 2 points P and Q, then they might not be in the normal neighborhood, in this one normal neighborhood. And so Q might not be even in the normal neighborhood of P.
So it's like you mean that this holds in only locally.
Well, in this case, you can. So the argument would be to use compactness of this segment, the 0, 1.
So like
Right, so you can actually cover like you have finite number of points, right? Numbers between 0 and 1, such that corresponding normal neighborhoods cover your,
Yeah.
and in each you have equality of length on
Yeah.
geodesic, but geodesic is actually local, local condition to be geodesic. Well, so you just do what you
Okay.
need, like in every
we can glue them and
Yes.
in a more.
You can prove like that it is geodesic in every piece of it, then
And then-
therefore it's geodesic. Yeah, because like being geodesic is a local condition, actually. So that's what I'm saying. Okay. So I don't know. Should we stop or should we talk about linear? I don't know. Nobody did it because they just were not interested in long enough problems, or because there was some technical problem. Should not be any tricky part. So if you have any question about it, let me know. Otherwise, let us just.